Hello and welcome to some step response level 2 questions. First one. Right, we have here a first order response and we don't know where it's heading to, but we could try and do some curve fitting and work out what the time constant of this is. That might be a useful thing. Let's have a quick look at the circuits to see if we actually need to do that. Well, if we look at this circuit here, we can instantly eliminate it. Since at an infinite amount of time, when the steady state has been reached, there will be no change in current and therefore no voltage across this inductor. That means that we have here a potential divider which just divides by 2. And with a 1 volt input, that would give us a 0.5 volt output. But the output here has already gone above 0.5 volts, so we can eliminate C. Number D, we can eliminate for the same reason. In the steady state, when the capacitor has completely charged up, we can ignore its effect at infinite time, and we would expect X to be half of A. However, the output here has already gone above half of the 1 volt input, so we can eliminate D as well. That leaves A and B. We can eliminate B as well by thinking about what happens at time t equals 0. At time t equals 0, we can consider the inductors to be open circuits and capacitors to be short circuits, and that would just give us a circuit where A is connected to X via a 100 ohm resistor. So we would expect the step response for circuit B to shoot up to 1 volt and then start coming down, which clearly it doesn't. So, having eliminated B, C and D, the only possibility left is circuit A. Great. Next. Another one like this. Well, here we've got a step right at the beginning, but it only goes as far as 689 millivolts, and then we start building up from there. So, obviously something interesting happens at time t equals 0. Consider time t equals 0, and at that time we can consider all inductors to be open circuits and all capacitors to be short circuits. So this circuit here, A, would effectively have an open circuit there, and X would remain at 0 at time t equals 0. Can't be A. This circuit here, B, well, A would be directly connected to X, so we would expect a step response which shot straight up to 1, because that capacitor would be behaving like a short circuit. Here, A and X at time t equals 0, the capacitor is behaving like a short circuit. We would expect X to be connected to ground and it to start gradually moving up as the capacitor charges up. So we've eliminated A, B and D. The only possibility left is C. And you can sort of see how that would work. At time t equals 0, the capacitor is a short circuit. We've just got a potential divider with 4K7 at the top and 10K at the bottom. So we would expect the voltage at X to shoot up to 10K divided by 14.7K, which would be 680 milli, which is exactly what it does. And after that, as the capacitor charges up, the voltage on X will start to slowly increase, which is the shape that we're seeing. So the answer must be C. Well, this time we have to build the circuit. And we don't know the value of the resistor, but we do know that the circuit is going to start off with no output at all just after the step has occurred at point A. So this must be in this arrangement. So that at time t equals 0, or just after time t equals 0, there will be no current flowing through the inductor. The output X there will still be at 0. To work out the value of the resistor, we need to consider the time constant here. The the good old 63% rule. We are at 63% here at approximately 1.4 milliseconds. So we have that 1.4 milliseconds must be L over R. So R must be L divided by the 1.4 milliseconds. And that's about 15.7K. These are always E24 series resistors, so 16K I reckon is the most likely value. Great. See if I can just do one more. Right. This is a bit trickier because we can't see what the time constant of B, C and D are very clearly. Well, let's have a look. Actually, we don't need to. You could just consider what this circuit looks like after a very long time. And after a very long time, when everything is settled down to the steady state, there will be no change in current through the inductor, which means no voltage across the inductor. We can consider it just a short circuit after a very long period of time. And in that case, we've just got a potential divider with a 3K3 here and a 3K3 there, which means our output should be half of the input. And only one of these looks like it's going to get anywhere near 0.5, and that's A. So A. Fine. And so on. So that's level 2. They are a bit trickier, but if you remember those 3 useful rules. The time constant is the time it takes to get 63% of the way to its final value for a first order circuit like this. The behavior of the circuit just after the step has arrived at the input can be determined by treating all inductors as open circuits and capacitors as short circuits, and the behavior a long time after the step has been introduced can be calculated by assuming that the inductors in their steady state are short circuits, they have no voltage across them, and capacitors in the steady state are open circuits, they have no current flowing through them. That's about it. Good luck.